There we go. Okay, so in the Q&A so far, I posted how to do problems 1 through 46, the even ones. And rather than go over those again, I'm just going to continue from number 48.
I have questions from the homework.
Go ahead.
If we could do a couple of those first.
So which problems are you talking about?
1, 2, 3, maybe 4.
1, 2, 3, and all of them?
I have like little like questions about each one. But...
Well, let me pull up the homework to see what questions you do have, okay?
Okay.
Because I don't remember what's in the homework. Okay, so I see I don't have these separated into 1, 2, 3, and 4. They're just listed. So what question do you have about the first one, where we're going to be taking a look at it in just a second?
So I thought it was pretty simple after I asked you about how to get speed. But when I went through my calculations, what I got doesn't seem correct for the specific heat capacity of lead, because then I Googled it and it wasn't close to that.
What did you get?
I got 3,120 joules per gram per degree Celsius.
Yeah, that's not close. Okay, so what I'm going to do is I'm going to read the problem and I'm going to write down some things from the problem, and then I'll share my paper with you so you can see what I have. All right?
Okay.
So I'm going to write down that the mass of the lead is 27.3 grams. And I'm going to put the initial temperature of the lead is 98.90 degrees Celsius. And I'm going to put that the final temperature of the lead is 26.32 degrees Celsius, because when the water levels out at 26.32 degrees Celsius, that means the lead is also the same temp due to thermal equilibrium. Now for the mass of the water, I'm going to put 15.0 grams. For the initial temp of the water, I'm going to put 22.50 degrees Celsius, and the final temp of the water is going to be 26.32 degrees Celsius, and we're supposed to determine the specific heat capacity. So I'm going to do a different share with you now, and what you should see here are all of those numbers that I just read to you, and I'm going to zoom in on this just a little bit. And how does that look?
It's a little blurry.
It's perfectly clear on my end.
Blurry.
Have you guys seen the optometrist lately?
No.
So I got 20/20 eyesight. Oh, there we go. Oh.
Is that better?
Yeah, it's perfect.
Okay,
yeah.
I did an autofocus. So clearly I'm messing with you. All right. So the idea here is that the heat represented by Q of the lead and the heat of the water is equal to 0. And so when I say Q of the heat of the lead, Q of the water, I'm talking about this. Here's your lead, here's your water, and this one starts off hot and this starts off cold. You put them together, and this is going to be like the instant you put them together, not after they've settled. We're talking the instant you put them together. You see this little air that goes from the lead to the water? That is heat energy flowing from the lead into the water. And then after time, what happens is no more heat flows. So what's going to happen to the temperature of the water as heat enters it? It will rise. What happens to the temperature of the lead as the heat leaves it? It will lower. And so they're both the same temp. All right, so, if I wanted to put in some more, I'd put in like a 26.32 for both here. And I put 22.50 here and 98.90 here. And then here, we're going to say that this is the same as before, because this is the instant they mix. All right. So this is a very important drawing because this shows you that the amount of heat that enters the water is equal to the amount of heat that leaves the lead. Now, since the heat is leaving the lead, it's actually a negative value. Exothermic is a negative value. So we would say negative Q of the lead because it's a negative value. Now, the heat entering the water is endothermic and therefore it has a positive value. And I'm not going to put a positive there, but I guess I will. Now, what do we know about these amounts numerically? They're the same. So if this is negative 10 joules, this is positive 10 joules. No matter what amount of heat it is, it's the same for both numerically. And since they have opposite signs, what happens when we add them together?
Cancel out.
They will always equal 0. And that's the origin of this formula, which is really important for these problems. Okay, the other thing you need to know is that when you have a change in temp, the way to calculate the energy change is Q is equal to Cm delta T. I sometimes tell people it's Q equals MCAT because it's an easy way to remember it if you're going to take the MCAT in the future, which is a test to get into med school. But this is the way I learned it, and I kind of like it this way better. CMAT.
I like MCAT.
Pardon me? You like
I like
MCAT? Well, I think that's because I told you that. But this is the way I learned it. Okay. So here, if we plug this formula in for each of these carefully, we can figure this out. So I'm going to view Q of the lead. And what I'm going to do actually is I'm going to put this piece of paper to the side and refer back to it. So I'm going to have Q of the lead plus or is equal to 0. And then I'm going to put C of the lead, mass of the lead, change in temp of the lead, plus C of the water, mass of the water, change in temp of the water is equal to 0. And then I'm going to rearrange this all at one time. I get the specific heat capacity of lead, which is what we're looking for, is negative C water, mass water, change temp water, divided by mass of the lead and the change in temp of the lead. So the change in temp of the water is going to be the T final minus T initial. And I'm going to put W out here for the water. The initial temp of the water, well, the final temp is 26.32 degrees Celsius. The initial temp is 25.0. Oh, I'm sorry, 22.50 degrees Celsius. So when we do the difference here, 2 minus 0 is 2. 3 minus 5 is going to be 8 because we're going to borrow 1 from the 6. And now that's a 5 minus 2 is 3. And then 2 minus 2 is 0. So that change in temperature for the water is 3.82 degrees Celsius. And notice, even though we started off with 4 significant figures here and 4 here, because we're doing subtraction, we're going to use precision to decide how many significant figures we have here. This is precise to the 100th. This is precise to the 100th. So this is precise to the 100th. When they're both the same, the precision matches the original. And notice we only have 3 significant figures here. Capiche? So we do the same for the change in temp of the lead. But remember here, the final temp of the lead is still 26.32 degrees Celsius. We do not put 98.90 first, just because it's bigger. You put the final temp first. So 98.90 degrees Celsius. And so I'm going to take 0 minus 2 is 8. I have to borrow 1 from the 9. So that becomes what? 8 minus 3 is 5. And then I have 8 minus 6 is 2. And 9 minus 2 is 7. And these are also good to the 100th. So this is good to the 100th. So this still has 4 significant figures. Are you with me there?
Mhm.
So it's good to do your temperatures off to the side. So now to get the specific heat capacity of the lead, I'm going to use all of the numbers that I need. For the specific heat capacity of the water, you should memorize it because it is exact. And we're going to use 1 calorie per
Tony,
gram degree Celsius.
is
Yeah.
it delta T negative?
What's that? Oh, yes.
Okay.
Now, what is the mass of the water?
Maybe
15 grams, right?
Mhm.
And then what is the change in temp of the water? 3.82 degrees Celsius. And I like to put parentheses around each one of these just to kind of separate them. The mass of the lead was 27.3 grams. And the change in temp of the lead was minus 72.58 degrees Celsius. And if we take a look at this, can you see how the degrees Celsius cancel here? The grams cancel here. And our units are calories per gram degree Celsius. Those will be the final units. So I'm going to put that over here. And I like to estimate the rest of this. So here's how I do it. That's 4 because it's close enough to 4 for me. 4 times 15 is 60. I know this is not going to be 60, but I'm okay with that. 27 goes into 60 how many times? Twice. I know it's not twice, but it's close enough for me because, heck, I know that's not 60. It's less than 60. So 27 goes into something that's less than 60 twice. It's beautiful. Now I have 2 divided by negative 72, which to me is like 1 over 35. 2 over 72, 1 over 35. And I think 35 goes into 103 times, so that's like 0.03. So that's my estimate. So let's see what we get. Now, if you're trying to look for the answer online, they don't usually tell it to you in calories. But since this problem did not specify the units, I'm going to do it in calories. Okay, so I get 0.0289 calories per gram degree Celsius. And the reason there are 3 zig figs is because of the 3 here, the 3 here, the 3 here, the 4 loses. This is exact because it is defined. So that's your answer. Now, if we wanted to convert that into joules, we would take this number times 4.184 joules per calorie. And I get 0.121 joules per gram degree Celsius. And you also need to remember that this degree Celsius is interchangeable with K, not because they are the same unit, but because the size of each is the same. And because the size is the same, and because the temperatures are found by changes in temperature, a change in degrees Celsius is equal to the same change in Kelvin. So what would I expect to see on an exam for this? I'd expect to see all of that. Now, it is okay to use 4.184 here, but 4.184 has 4 significant figures. And that's why I don't like to use it. It's not as good as 1 with an infinite number of significant figures. Okay, so if you're getting a really huge number, Charlotte, I think it's a if you don't have this set up this way, then you might try doing it this way. Also, if you do have it set up this way with these numbers, check and see if your numbers are the same as these. And lastly, if you do have these numbers, you're not using your calculator correctly.
Well, my question now is, so I understand the calculations and where the numbers come from, that's fine.
Yeah.
But conceptually, I don't understand. So how I approached this problem was, to me, it sounded like the information for the water, like the math, was just kind of extra information. So I just solved the problem with the data provided for lead.
And you can't do that. Because conceptually, if we go back to the description here,
Right.
You have to understand that the Q's are the same. And if you take a look at all of this information here, you have the initial mass of the water, you have the change in temp of the water. I can even write C for the water is 1 calorie per gram degree Celsius. And here I can write C for the lead is what we want.
Right.
So when you consider that you have all this information for the water, that's your bedrock for solving the problem. This one says, okay, you know what? I have this formula here. I have C for the water. I have mass. Oh, I'm going to the wrong one. This should be over here. You see how I put those in the wrong places?
Yeah.
But for the water, we have the specific heat capacity. We have the mass. We have the change in temp. We can calculate the Q. Then from this formula, we could get the Q for the lead. And then, you know, we could do it in 2 parts. It's a time saver if you do it all at one.
So we need Q of the water first.
Well, you need this Q.
Mm-hmm.
And the Q is the same size, but different sign for lead versus water.
Okay.
So how do you figure out how big Q is when you don't know the specific heat capacity of lead from the lead information? And the answer is you can't. So how do we figure out Q of the water, considering we have all the information we need? We use, as you like it, Q equals MCAT. So if you wanted to, you could look at this another way. We could realize, first of all, that Q of the water plus Q of the lead is equal to 0. So this is basically starting the same way. Q is equal to Cm delta T. And when you look at lead versus water, water is the one where you have everything. So you can do Q of the water is C of the water, mass of the water, change in temp of the water, which is 1 calorie per gram degree Celsius, 15.0 grams. And the change in temp of the water, I need to flip my paper over to find that, was 3.82 degrees Celsius. So here, when we're done with this, do you see the grams cancel and the degrees Celsius cancel? And 15 times 4 is about 60. So this answer better be close to 60, but a little bit under, right?
Yeah.
And I get 57.3. And that's going to be calories. So now we use this formula. So that's kind of like the first calculation. The change in temp is kind of like a pre-calculation.
Yeah.
So Q, the second calculation, we're going to say Q of the lead is equal to negative Q of the water because of this equation here. So I'm going to say Q of the lead is equal to negative 57.3 calories. So there's my second calculation. Not really a calculation, just a substitution, if you will. And then my third calculation is Q of the lead is equal to C of the lead, mass of the lead, change in temp of the lead. But in this case, we don't want Q of the lead, we have it. We want C. So C of the lead is Q of the lead over mass of the lead, change in temp of the lead. And when we plug all these numbers in, we get negative 57.2 calories, 0.3 calories. The mass of the lead was 27.2 or something like that. 27.3.
Yep.
And the change in the temp of the lead was 70 something, right? Negative 72.58 degrees Celsius. And here you see how the negatives cancel each other and they become a positive.
Right.
And let's see, what kind of answer should we get? How many times does 27 go into 57?
Twice.
Twice. What's 2 over 75? It's the same as 1 over 35, which is 0.03.
Mhm.
So I get 0.0289 calories per gram degree Celsius. And it's the same answer as before, not quite as elegant because we're doing 3 different things all in order, right? You got to do this first, then this, then this. And this is just putting it all together in one little solution and doing a little algebra here. Okay, but you'll notice the answer was the same. So for a problem like this, this consumes to me a lot of time, and so I don't like doing it. But if you showed me this work well organized along with this equation up here, I'd be fine with it.
Would it still result in full points, or would you say?
Well,
no?
as long as you have the correct number of significant figures, you have your units in your solution, you show the original formulas,
Okay.
then yes. Okay, but you don't leave the units here. You don't organize it well. Like here, we can see how well this is organized. Which calculation should we look at first?
1.
Number 1. Okay, because that's the way we do it. We go from smaller number to larger number, right? We don't start at 3, we start at 1. Okay. Now, that is the first one. Are we good, Jacoby? You good on all this so far?
Yeah.
Let's look at the second one. So I'm going to change my share to the problem set, and we're going to look at number 2. Or I should say the second problem. So we have insoluble lead 2 bromide precipitates when a solution of lead 2 nitrate and sodium bromide are mixed. And here you have I think it's a balanced equation. To measure the enthalpy change, you basically mix some of the lead 2 nitrate with some of the sodium bromide solutions in a coffee cup calorimeter. Now it says the temperature of the mixture rises by 2.44 degrees Celsius, right?
Mhm.
Calculate the enthalpy change for the precipitation and assume the density of the solution is blah, 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 and its specific heat capacity is 4.2 joules per gram per K. So what can we say about this? I am going to write some of this information down before I switch screens.
So my question was this one. This is a constant pressure problem, correct?
Right.
So in the example from the lecture, from example 5.7 in the textbook,
Uh-huh.
I kind of use that as my guideline. But
Okay.
that one only has like one compound. So it was more simple. With this one, I was getting confused about, I mean, I guess it asked for lead bromide. It just seemed a lot more confusing than the example from the book.
Well, let's take a look here. Oops, I wrote down the wrong thing. What does it say the density is 1?
Yeah, 1 gram
Yep.
per milliliter.
And we're going to say the specific heat capacity of the solution is equal to 4.2 joules per gram K, which we also get to write as 4.2 joules per gram degree Celsius. Okay, so I'm going to do a switch screen. Okay, now you saw on the previous problem, I like to start off with Q plus Q equals 0, right? So here you have this solution with lead nitrate, lead 2 nitrate, and you have the solution with sodium bromide. And they don't tell us what the initial temperature is. I don't know what it is.
Right.
When you mix these together, so I need a bigger cup here, we get lead bromide solid, plus we have sodium nitrate. Now, here's one thing we do know is that the change in temp was 2.44. So basically they're telling us this is 2.44 degrees Celsius greater than these. So it really doesn't matter what this temperature was. I know that this temperature is 2.44 degrees Celsius. If anything, the one thing I do find out is that these were at the same temp if they're both greater by 2.44 degrees Celsius. Now, how difficult would it be to get these to be the same temperature? And the answer is not difficult at all. Put them in cups and leave them in the room for a while until they both get to be room temperature and they're the same temp. Are you with me there?
Yeah.
I'm gonna grab a notebook.
Okay. So in this case, since they're the same temp, when you mix them together, they're not going to make the solution warmer. Because two cold solutions should not make the total warmer. So what's providing the heat? The reaction. The reaction is providing the heat. So we would say Q of the reaction plus Q of the solution is equal to 0. Now for Q of the reaction, there are no specific heat capacities for reactions. There are no masses for reactions, so to speak. There are no, well, there are changes in temperatures, okay? Now for Q of the solution, we're treating this like water. It's really clear to me that we're treating this like water for 2 reasons. They tell us the density is 1 gram per milliliter, which is the density of water. And they're telling us the specific heat capacity is 4.2 joules per gram degree Celsius, which is really close to 4.184 joules, which is the specific heat capacity of water. So they're basically saying, you know what? The solution is so close to being water, let's treat it like water. So of these 2 things we can do, what can we do first? Can we get the Q of the reaction? No, but we can say this. Q of the reaction is negative Q of the solution. Can we do this? Q of the solution is equal to the specific heat capacity of the solution, mass of the solution, change in temp of the solution. That we can do. And if I make a little list up here of things, I already have that the specific heat capacity of the solution is 4.2 joules per gram degrees Celsius. The mass of the solution is going to be their volumes, 200 mils and 200 mils, that's 400 mils.
So we would add those together.
Yep, because
That's
this solution is 2.44 degrees warmer, which means all 400 milliliters has absorbed heat.
yeah.
So I'm going to put 400 milliliters times 1.0 gram per milliliter, which is 400 grams. And what is the change in temp of the solution? It's right there, 2.44. And when I estimate this, I basically think 2.44 times 400 is 1,000. It's really close to 1,000. So 1,000 times 4.2 is 4,000. And indeed, I get 4099 joules. And this is only good to the 0, but I'm not going to round yet because we're not supposed to round early. Now, what's the second or the third thing we do? So I'm going to put number 3 over here, even though I have 1 and 2 over here. Number 3 would be that Q of the reaction is negative Q of the solution, which is equal to negative 4099 joules. And I'm going to put a little arrow there also. Now, what does the negative mean? It means that the reaction produced heat. What happened to that heat? It heated up the solution. Now, they do ask us per mole of lead nitrate, right? Let me go back and look at the problem. So they want to know what is the change per mole. They want kilojoules per mole of lead to bromide. So if only there was a way for us to calculate the moles in this reaction. Is there a way for us to calculate the moles in this reaction?
Yeah.
How do we do it?
So you take, what is it, the moles with your reactants and your products?
But we're not given the moles. We're given the milliliters and the molarity.
Yeah. Sorry, but we know that the solution is what? Close enough to water?
We know it's close enough to water, but we need the moles of lead bromide. So what we have to do is this. We can take our 200 milliliters of lead nitrate, multiply that by 1 liter of lead nitrate per 1,000 milliliters of lead nitrate. Now, the reason I'm doing this is because I want to use the molarity of the solution. The molarity of the solution is moles per liter. So here I have milliliters, and if I want to use moles per liter, I need to take that and change it into liters. So now I can use this concentration of 0.75 moles of lead 2 nitrate per 1 liter of the lead 2 nitrate solution. So that gives me moles of lead 2 nitrate, but you know what? I'm not going to stop there. From the balanced reaction, there's 1 mole of lead bromide to 1 mole of lead 2 nitrate. So if I go back and look at that balanced reaction, those are the proportions. So let's see how many moles of lead 2 bromide we get. So I'm going to estimate again. How many times does 200 go into 1,000?
Was it like 5?
5. What's 0.75 over 5? Here's the way I think about it, because I don't like to do too much work in my head. If it were 1 out of 5, I could do it. 0.2, right? So 0.7 over 5 is not 0.2. It's going to be like 0.15, a little bit less. So let's see what we get. Oh, damn, it is 0.15, isn't it?
Mhm.
How many significant figures?
2.
There's 2, right?
And it's 0.150 if we kept extra digits.
Mhm.
So 0.15 moles. But how do we know that all of this reacts? Well, what we're going to do here is we're going to take our 200 milliliters of sodium bromide and do the same thing. How does this differ from the previous problem? And you're going to see in just a minute where it differs once I get my big fat hand out of your way. So right here, I'm changing the milliliters to liters, but the molarity is not 0.75, it's 1.5. So the molarity is different. And the stoichiometry is different. It's not 1 mole. Well, it is 1 mole of lead bromide, lead 2 bromide. But in the balanced reaction, it says 2 moles of sodium bromide. When we do this and do the calculation, we get 0.15 moles of lead bromide. Now, when we calculate these two numbers, whichever number is the smaller, that's the limiting reactant. Since these numbers are the same, that tells you that these are being mixed in the precise proportion so everything reacts. So now we get to take our negative 4099 joules over 0.15 mole of lead 2 bromide, and they want kilojoules per mole. So what am I going to multiply by? And the answer is 1 kilojoule per what?
1,000 joules.
1,000 joules. And so I'm going to estimate this. What's 4,000 divided by 1,000?
You think 4.
4. How many times does 15 go into 4? Well, I don't know, but it goes into 1 about 6 times.
Mhm.
So 6 times 4 is 24, but maybe a little more. So maybe the answer is like 27, 28.
Mhm.
Okay. Kilojoules per mole. Let's see what we get. And I know for certain it's going to be negative. And I want to put this little arrow here because I know that that should have been rounded there if I wanted to round. And I get 27. So if you look at the genesis of this problem, it started where all of the others started. Q's. You have to decide what are the things that are sharing the heat. In this case, it's the reaction and the solution. And this is novel to us because before we had concrete things that are sharing the energy, right? Water and water, water and a rock. And now we got water and a reaction. You know, it's a Scooby-Doo moment. Can you do that? Absolutely. Okay.
Yep.
So there we go. Does that help at all with that one? Yeah. Okay. I'm going to change the share. Let's take a look at the third problem. What quantity of energy in joules is required to raise the temperature of 454 grams of tin from room temp to its melting point and then melt the tin at that temp. The specific heat capacity of solid tin is 0.227 joules per gram per K, and the heat of fusion of tin is 59.2 joules per gram per K. So I'm going to write some things down here before I change my share, because I won't be able to see these things once I change my share. Okay, and then okay, now I'm going to change my share. Okay, so I've done some problems like this in the Q&As. Here's what's going on. The tin is staying tin, so there's no reaction. Fair enough? So I'm going to draw a little diagram here that shows energy and temp. Now, I'm not going to try and draw it to scale or anything like that. I just want to capture what's happening here. So the tin starts right here at 25 degrees Celsius. And we put energy in until it gets to 231.9 degrees Celsius. So the temperature rises. During this time, the tin is a solid. So do we understand this part of the graph? It's just showing the temperature change of the tin.
Yeah.
What happens when it gets to 1.9 degrees Celsius? It melts. When it's melting, you will have solid tin and liquid tin together. And since they're together, what do you know about their temperatures? They're the same. They're the same. So when there's just a lot of solid and a little bit of liquid, as the solid goes away and it becomes a lot of liquid, their temperatures stay the same. So that means the temperature does not change. So we got two parts of the graph here, the rise and the flat part of the graph, right? Now, in this flat part of the graph, the change in temp is equal to 0. And in this rise, the change in temp is going to be 231.9 degrees Celsius minus 25.0 degrees Celsius, which is going to be 206.9 degrees Celsius, if I got it right. Does that look okay? Mm-hmm. All right. So we want to calculate how much energy it takes to warm up the tin and how much energy it takes to melt the tin. So we have two types of equations. If there is a change in temp, so if the change in temp is equal to some number greater than 1, right? Greater than 0, then we use this formula, Q equals Cm delta T. And if the change in temp is equal to 0, then we use Q is equal to the heat times the mass. Now, what do I mean by the heat? Well, it depends on the change. If you're melting, you use heat of fusion, which is what they gave us. If you're turning it into a gas, you use what's called heat of vaporization. So I use the general formula, heat times mass. So this is when you're heating something, and this is when you have a phase change. Because during a phase change, there's no change in temp. Okay, so let's do the change in temp one first. I'm not going to write Q of the tin because everything here in this problem refers to tin. So specific heat capacity is 0.227 joules per gram degrees Celsius. And then we have the mass of the tin is 454 grams. And we have the change in temp of the tin is right here, 206.9. And we can estimate this. For instance, I know that's not 1/4, but it's really close, right? So I'm going to say, what's 1/4 of 400? 100. What's 100 times 206? 20,600. How many significant figures would we be allowed?
3.
Yes. So we would have 2, 1, 3, 2, 3 joules, and that's where we would round to, the first 3. The second part would be Q here, which is going to be 59.2 joules per gram degrees Celsius times 454 grams. Oh, and I made a mistake. I added that and it's not there.
That was my question with this problem.
But it's not there, right?
In the problem, it's given as with grams and Celsius on the bottom.
Is it?
Yeah, so I had Celsius on the bottom and it didn't look right.
Well, I'm going to edit that.
And that was why I was confused with this one. So that's good. That makes me feel better then.
Well, I got to edit this even more because I have points are 10 and you need to turn it in. The points are 0.
Yeah, I was confused on that. I saw it and I was like, what in the world? I was like, oh, it's probably just.
Well, it's because last semester I collected homework. I'm not doing that anymore. I don't have time to grade your freaking labs. Well, I'm going to have to edit it later. So what's 59 times 454? The way I do this is 60 times 400. So around 24,000. How many zig figs are we allowed?
Still just
3.
3, right?
3.
Mm-hmm.
So then we just add these two numbers together.
Okay. Would we round after adding?
That's right. And so I get 4, 8, 2, 0, 0 joules. So that's how much energy it would take to do all of this. And so you can see you would actually use more energy to melt this stuff than you would to change its temp. And that's not unusual. A lot of times it takes more energy to do a phase change than it does to warm something up. Any questions on that one?
Nope.
Okay, I'm going to put that off to the side. You said the first 4, so let's look at number 4, if I remember correctly.
Yeah.
Okay, so I need to go back to the problem set. This is the bomb calorimeter one, right?
Yeah.
Okay, so a bomb calorimeter was run to determine the enthalpy of combustion of ethanol. So this is one of those ones where the reaction produces heat. The bomb had a specific heat capacity of 550 joules. Calorimeter contained 650 grams of water, blah, blah, blah. So I'm going to write some information down. The heat capacity of the bomb is 550 joules per K. The calorimeter has 650 grams of water. We have 4.20 grams of ethanol. And we have a change in temp from ended at 22.3 degrees Celsius and it started at 18.5 degrees Celsius. And they ask us to calculate the internal energy, which is basically the heat for this reaction. The internal energy is actually a sum of the heat and the work. But because this is done in a constant volume, there's no work. So when they ask for the internal energy, it's really kind of silly. It's all heat. And that's the purpose of it being a bomb calorimeter. No change in volume, no work. And the bomb is a very rigid container that does not change its volume. So for some reason or other, this guy got influenced by some physicist who said, oh, you ought to actually write this. Okay. And then we want kilojoules per mole. Okay. I'm going to change my share. Okay, so here's all the information I've written, and this is what we want, right? So if we think about this, we want kilojoules and we want moles. Is one of these easier to do than the other?
Yeah.
Yeah, I would say moles.
I'd say getting the moles, right?
That seems easier to me, yeah.
So let's do it. We have 4.2 grams of ethanol. That is a common abbreviation for ethanol. If we look at the molar mass of ethanol, 2 carbons is 24.02, 6 hydrogens is 6.06, 1 oxygen is 16. So 46.08. So here, this is clearly going to be close to 0.1 because it's 4 over 4, but a little less than 0.1. So maybe 0.08 or something, 0.09. We've got half the problem done. We've got the moles. I know it's not the harder half, but we got half of it done. Mm-hmm. Now, how do we get the kilojoules? So let me make a drawing for you so you can see what happens. So what's going to happen is the reaction is going to produce heat. So you got Q of the reaction. So we're doing number 1 here now. When that reaction produces heat, what's going to happen to the bomb? It's going to heat up. What's going to happen to the water? It's going to heat up. So we have Q of the bomb plus Q of the water. And for the bomb is loosely everything that's attached to this thing that's not the water. So it includes this container on the outside. It includes any transfer that may happen to the air. The bomb is everything else that's not the water and not the reaction. And there's our formula. Which ones of these are going to be easier to calculate? Q of the bomb and Q of the water. Let's do Q of the water. Specific heat capacity of the water, mass of the water, change in temp of the water. So here, because they want it in joules, we're going to use 4.184 joules per gram degree Celsius. The mass of the water is 650 grams. The change in temp, according to this, is 22.3 minus 18.5. 3 minus 8, or 5 is 8. And then we have 11 minus 8 is 3, and then 1 minus 1 is 0. So 3.8 degrees Celsius change. So if I estimate this, what do I get? This was a tougher one to estimate, agreed? But what if we do this? That's 4, and that's 600. What's 4 times 600? 2,400.
Yeah, 2,400.
But what if that's more like 700? What's 4 times 700?
It's going to be
2,800, right?
Yeah.
What's halfway between 2,400 and 2,800?
2,600.
2,600. What's 2,600 times 3.8? Well, forget that. How about 2,600 times 4? Or let's make it even easier. Let's make it 2,500 times 4. Because 2,600 isn't too far from 2,500. What's 25 times 4?
Around 10,000.
Yeah, that's 25 times 4 is 100. Then add the 2 zeros and you get 10,000. And I get 10,334 joules on my calculator. So I must be pushing the buttons correctly. Now it's actually calculating Q of the bomb is even easier. Now take a look at the Q of the bomb. Do you see how that says 550 joules per K, which is the same as 550 joules per degree Celsius? If we want that to end up being joules, what do we have to multiply by to make that happen? Do we have to multiply by mass? Would mass make that degree Celsius cancel?
No.
No, so let's not multiply by mass. Do we want to multiply by a temperature?
Right, yeah.
That would make the degree Celsius cancel, right? What temperature do you think we should multiply by? 22.3, 18.5, or the change in temperature?
It's going to be the change, right?
It's the change. Because this is how much energy per 1 degree Celsius. So how much per 3.8? Well, we do this. So do you see how this calculation is actually easier than the one above?
Hey, Tony.
Yeah.
So my confusion with this one when I was doing it on my own earlier was, why do we not have a mass? Why do we not use the mass for the bomb?
You don't need it. The bomb has a particular mass already, okay? That doesn't change during the experiment. And naturally, the bigger your bomb, the more energy it takes to warm up, right? But since we're using the same bomb, they take mass out of the experiment. They say that, well, you know what? The mass doesn't change on the bomb. but the temperature will. Does it make sense that the amount of energy for 1 degree is going to be about the same? And it does, right?
Yep.
Yes.
Okay, so if the mass of the bomb doesn't change, we don't really care about how big it is. We just care about what its temperature change is.
Mhm.
So it's kind of like for you, to heat you up by 1 degree Celsius might take a certain amount of energy, right?
Mhm.
And then if we have someone who's twice as big as you, they'll probably take twice as amount of energy to heat up by 1 degree Celsius.
Mhm.
And you and another person would have different specific heats. So this specific heat takes into account this particular bomb, and we don't need the mass. Okay, so here I think it's 500 times 4, which is 2,000. And I get 2,000. Okay, so that's the number 1 part. Now, what's the, well, actually, I think this was 1. Or no, this was 2. This was 1. And then there's 3. Now, what do you think Tony would think of you writing out a problem like this on a test this way? I'd say you suck. This is horrible. And I take a point away for organization. Okay, for number 3, since we want kilojoules per mole, we can now take this, well, there's a trick. Q of the reaction is negative Q of the bomb minus Q of the water, which is equal to negative 2090 joules, which should be rounded at that 0, the first 0, minus 10,334 joules, which should be rounded at that 0. So why do I say this would be rounded to that 0? Well, look at how we got this number. We use 4.184, 650, and 3.8. 3.8 has only 2 significant figures, and so does 650. So this would be rounded to 10. And we'd have to write it in scientific notation. But we're just keeping track up here. So let's see what we get when we add these numbers together. I get 12424 joules. Where do we round this to?
Back down to 2, right?
The what?
Back down to 2, right?
1,000?
We round it to there. So do we see that this is 1, 2, 3, 4 places to the left of the decimal?
Mhm.
This is 1, 2, 3 places to the left of the decimal. The farther you are from the decimal to the left, the less precise.
Mhm.
So we would round to this place, which I call the thousands place. So how do we round 12,424 to thousands?
Gonna
It'd be
say
12,000, right?
Yep.
But we're not going to round yet. You know why?
'cause we're not done.
Because we're not done. So now we have negative 1,200, 424 joules, arrow to that 2, divided by 0.09115 moles. And this arrow goes to that one. Now, since we're doing division, we count zig figs. This gets 2, this gets 3. So how many zig figs are we left with?
Well, it's just gonna be 2, right?
2. Now, does it say kilojoules per mole?
Yes.
Yeah. So I'm going to go ahead and multiply this by 1 kilojoule over 1,000 joules. And now I'm going to estimate. What's 1,200 divided by 1,000?
Just 12.
Pretty close to, well, I'm sorry. Yes. 12. Right?
Mhm.
What's 12 divided by 0.9?
Oh, 0.9.
Well, why don't we just pretend that's 0.1? What's 12 divided by 0.1?
Oh, 1.2.
How about 120,
120, sorry.
right? So this is
Mhm.
not 0.1, it's smaller than 0.1. So we should get an answer bigger than 120, maybe 130.
Mhm.
Okay, so let's see what we get. So there's your final answer, 140 kilojoules per mole, not 136, because we have to round to two significant figures. And guess what? Good use of time. We're going to stick a fork in it because it's done.
Okay, I'm done.
Fair enough? So does that help you to understand a few more things there?
Yeah, thank you.
You betcha. And I'm going to pause the recording now.